In this example, we have a bird sitting on a perch. When the bird jumps off and has velocity, conservation momentum suggests that the perch should kick back in the opposite direction and swing. So you can think of it like a pendulum in this case. Well, how high would that perch end up swinging when that bird flies off? Well, let's draw a picture. So it might actually be helpful to draw this picture from a side view, right? In this picture that they show you, the bird would actually be coming out of the page. So it's hard to see that perch swing. So I'm going to redraw this situation. Let's draw the bird on a perch. I'm not very good at drawing birds, so I'm going to steal a bird here. I've got a little Twitter symbol here. There's our bird. All right, that bird is sitting right here on the perch, and that perch has a little pivot point right here. All right, so there's the bird on the perch. This is our before situation, right? We have two objects, two different masses. You have the mass of the bird, and we know that is 160 grams. You're going to want to convert that to kilograms anytime we work with that. So we're going to divide by 1,000. You have the mass of the perch. The perch is 50 grams, or 0.05 kilograms. Those two masses are one and the same with the same velocity. The initial velocity is 0. Right? So this is our initial situation. This is our before a collision occurs. And in this case, it's not really a collision, right? It's kind of the opposite of a collision. I like to call it an explosion, right? But you really have two things that are together that are going to be apart after the collision. So let's look at this is before, and now let's draw that same situation after that bird has leaped off. I'm going to throw another bird out here, and now this bird has jumped off. This bird now has some velocity. They tell you the bird has a velocity of 0.3 meters per second. And as a result, the perch now has its own velocity, the velocity of the perch. All right, so this is the velocity of the bird after the collision, and this is the velocity of the perch after the collision. All right, so you have this perfectly inelastic collision in reverse, right? And conservation momentum suggests that the momentum of the system before the bird jumps off has to equal the momentum of the system after. Well, that momentum of the system is the momentum of the perch before plus the momentum of the bird before, and afterwards the perch has new momentum. We'll call that the final momentum, and the bird has some final momentum. And since momentum is mass times velocity, you can expand that even further. The mass of the perch, the velocity of the perch at the beginning, plus the mass of the bird, the velocity of the bird at the beginning, has to equal the mass of the perch, velocity of the perch at the end, plus the mass of the bird and the velocity of the bird at the end. All right, well, we also know that at the beginning they're both at rest, right? Both of these velocities are 0. So actually, before this collision, you really have no momentum, right? There's no momentum before. And afterwards, you have this perch, which is 0.05 kilograms, moving with some final velocity. In this case, we're expecting it to be a negative number, plus the bird is 0.16 kilograms, moving to the right, the way I've drawn it, at 0.3. Right? So really, we've set up this equation, and we can do a little bit of algebra, and we can solve for that final velocity of the perch. Right? And that gets us going in the right direction. That tells you how fast it's going to be moving, and we'll have another step to go from there. So let's clean this up. Let's do a little calculation here. The 0.16 times 0.3. This is going to be the momentum of the bird after the collision is 0.48. So get back into black here. This is plus 0.048. 0.05 V perch final. That has to equal to 0. I can subtract over that 0.048. I'm just doing a little bit of algebra here. And what we'll find when we divide both sides by 0.05, I find that there is a velocity of the perch at the end. Turns out it's going to be a negative answer, which I expect if I divide that by 0.05. That perch is going to be moving at 0.96 meters, 0.96 meters per second. So that perch is now moving to the left at 0.96. The bird's moving to the right at 0.3. And that kind of makes sense. The perch is less massive. So to cancel out the momentum, it has to be moving faster than the bird. Well, that only gets us partway there. What they really want to know is how high will the base swing above its original level? Well, now we need to think about just the swing. The swing is at some level, it's going to swing upwards. And I hope you're thinking, hey, we have one object moving. Boy, energy is a great option. So now that we know the velocity of that perch, let's look at this as an energy problem. So that perch, let's look at our before situation, right, or our initial situation. Now this perch is sitting right here. I'm actually, just from a visual standpoint, going to have it moving to the right now since it's only the perch. And it's moving with 0.96 meters per second of velocity. And then later, it's now going to be swung up here. It's kind of like a pendulum. And if it goes to its highest point, the velocity is 0 at this highest point. And we know that there is a height change. So that height from here to here is what they want to know. They want to know how high is that thing going to swing above its original position. All right, so this is our after. All right, or our energy at position 1 and our energy at position 2, right? And with conservation of energy, we can say that the energy at 1 for the perch has to be equal to the energy at 2. And, well, what kind of energy do we have at 1? Well, if we call that lowest point a height of 0, then energy at 1 is only kinetic energy at 1. And later, it's stopped moving and it's elevated. Well, it's GPE at 2. So that becomes 1/2 mv1 squared is equal to mgh at position 2. As is typical, the mass of the perch doesn't matter. It cancels. We know the velocity. 1/2 of 0.96, we can square that, has to be equal to g, which is 9.8, times that height at position 2. So I'm going to divide both sides by 9.8. And I can solve for the height at position 2 that this thing is going to swing. Take that value, let's square 0.96, let's multiply it by 0.5, and let's divide it by 9.8. And we should find that the height is 0.047, and we've been in meters, kilograms, and seconds, so this should give us meters. It might be more reasonable to convert that to a useful number like centimeters. And so I can convert and say that this is equal to 4.7 centimeters of height change. So again, this bird's going to jump off of this perch, and because momentum is conserved, any momentum the bird gains to the right, the perch should gain to the left. So you're going to get that kick. This is the same dynamic that happens when you fire a weapon or a gun. You get that kick from the gun because that bullet has velocity and therefore momentum, and you experience the kick of the gun backwards. Well, this is what's happened to the perch. And since that perch has momentum, that velocity, again, I flipped it around to move things to the right. That velocity to the right is going to allow it to move and elevate, and gravity will do work, and it'll convert it to GPE. So we get a great example here in this problem where we have conservation momentum with this perfectly inelastic collision in reverse, becoming an energy problem where we're watching just the change in one object as it goes from having kinetic energy to having gravitational potential energy.